It's up. Okay, we're up and going now. So, yep, I'm John Ensworth. Hi, everybody. Thank you for coming. So, yeah, this is a hit on quantum mechanics, and this is for, well, for fifth graders, but it's for the general public. This is no equations. There's creepy, weird things that we're going to talk about, because this is a weird world that we're entering tonight, but keeping it as non-technical as possible. So these are strange concepts, but it's not hard to get the basics down at least. Most importantly, this is reality. Everything that you have a name for and you yourself are made up of these quantum mechanical particles. And we'll talk about what those are in just a moment, but it's kind of relevant in that the fabric of stuff around you is quantum. As Einstein said, everything should be made as simple as possible, but not simpler. We'll try to do that. And then we're not sure exactly who said this, either Einstein or is it Louis de Broglie? All physical theories, their mathematical expressions apart, ought to lend themselves to so simple a description that even a child could understand them. So there's some heavy hitters there that think that all this stuff can be taught. So it says, ooh, look at that, Schuster, dogs are so cute when they try to comprehend quantum mechanics. So, and this one says, now turn the page. Yes, Jenny. Miss Appletine, in the 20th century, kids our age were only expected to learn stuff like numbers and letters. Mostly they just went outside and played. Jenny, kids in the 20th century used to eat crayons. Now, back to quantum physics. Progress never bodes well for kids. So. All right, so what we're going to hit tonight are three big parts of this talk. It's not a very long talk, so don't worry. The first part is the observations that we make when we look at tiny, tiny things. We're just going to see what we see when we look at things that are smaller and smaller and smaller. And we'll see that it's strange. And so after that, we'll go into two parts that talk about two different major ways that physicists try to make sense of this strangeness. Not all physicists are comfortable with this stuff either. Einstein wasn't. So if he wasn't comfortable with it, you're allowed to not be comfortable with it either. So what does this quantum word mean? Let's start pretty basic here. Well, it means a number of things, like discrete steps and stuff like that. But for this talk, we're going to basically have it linked to size. And we're going to play the video instead of go through this picture here. I can go back to this later, but this short little URL is to this great video. In the 70s, there was a video called Powers of 10 that was shown all over the place, schools and like that. It's a little outdated, and science has marched on beyond that. But someone came up with a flash version of this. So I'm going to go to the back and start this at about Earth size and then head all the way down. And we'll see your normal everyday world, and then we'll transition down to where things go quantum. Oh, thank you. And it's got cool little background music to go with it here. So there's the Earth, and now we're going down to many of the moons in the solar system, down to the sizes of states. We got Hydra and Desmonia and Nix being around some of the Kuiper Belt objects. There's Phobos and Deimos, moons of Mars. The Large Hadron Collider, Central Park, AM radio wavelength. And now down to 1,000 meters. Got the pyramids, the Gateway Arch, a football field, size of a 747, and a dinosaur. Keep it. Each circle that comes zooming out will be another order of magnitude smaller. Getting down to 1 meter here. So there's a human. Nothing quantum happening here yet. Here's a little shrew and a matchstick and an egg. Here's a microwave wavelength, how long electromagnetic radiation is at that frequency. Here's an ant. Bless you. Now down to a grain of salt, pixel in an LCD camera like in your phone. Smallest thing visible to the naked eye is this gray circle, and now we're down to silk fiber, droplet of mist, a white blood cell, a red blood cell. Now we're down to just about to enter where quantum effects start really mattering. We're down to viruses. There's ultraviolet light wavelength. And this little pause kind of tells you we are now going into the world of the quantum weirdness. Here's a transistor gate and a microchip. Here's human DNA. You can see in the lower right corner here, scientific notation showing you how many zeros are before the 1 and after the decimal point. It's getting pretty small now. Down to a water molecule, cesium atom. Now we're down to hydrogen and helium atoms themselves, smallest thing an electron microscope can see. As Richard Feynman once gave a talk on, he said there's a lot of room at the bottom. There's a lot of stuff down here. So here's a uranium nucleus, helium nucleus, single proton and neutron. And now we're going to be just among the weird little individual particles. And we're going to talk about those briefly a little bit later. After this, yeah, lengths are not exact. It's kind of based on the energy, but there's a weak force extent. Up and down quarks make up protons and neutrons. And you've got strange and charm quarks. I think quantum physicists name some of these things way late at night when they've had too much coffee. So. It's a zeptometer. You've probably never said, can you say zeptometer? There's a top quark. There's a yottameter. Something called a neutrino. Look how many zeros we're getting after the decimal point in a meter now. Very tiny. But we're still going. Plunging through the quantum world here. At some point I'll give a talk on string theory and try to bring that home. So maybe the third talk in the distant future will be string theory for 5th graders, but I don't have that on the drawing board yet. So we'll get down to that scale in just a moment. Still going, circle after circle. A lot of stuff happened in the early part of this video between each circle, but no, not until we get to this last bit do we see anything new and exciting. Now we're down to what's called the Planck length, and there's the size of a string in string theory, and something called quantum foam, which I'll have to talk about some other time. But a Planck length comes from this. If you want to see and measure stuff down this tiny, you have to use more and more energy to probe that far down. And once you get to the Planck length, if you could come up with a device that could focus enough energy to visualize that, the very energy that you're working with would pop into a black hole for a moment. So, oh, let's not start over. Bad video, bad. So if you want to see this part of the video, you can either go to the website and catch it, or you can come back for relativity for 5th graders that we're scheduling for about September of this year. So we'll go to the top end of big things then. So again, that's this little URL has that flash video that you can go scrolling in and out and have fun, or just sit and listen to the music until you fall asleep. All right, so this quantum idea also is related to strange behavior, and we're gonna see the world that you're used to and your intuition is connected to doesn't really prepare you for this. We're not wired to comfortably deal with the strange things that happen down at the quantum level. But let's start with an atom. Everybody's heard of the word atom, so that's a good place to start. Comes from Greek philosophers, just meaning something that's invisible. They philosophically thought there had to be an end to how much you could take a rock or a piece of wood and keep cutting it in half, keep cutting it in half. There's going to be an end you hit. And the idea of an atom still didn't get really accepted until the 1800s, where some observations started to become clear enough that people could say, yeah, I think there probably is something to this atom idea. Now what's really funny is that as soon as we got down to something that's indivisible and called it an atom, we have since found there's a lot of stuff inside of it, so it is divisible. So we've kind of messed up the word atom already. But Einstein again helped with the mathematics of atomic motion in 1905. He shows up a lot in this stuff. Einstein might have been smart, I guess. So there we go, the atom. Okay, wrong atom. Let's go to this atom. Very simple idea of an atom is you have protons and neutrons in the center. The protons have a positive charge. Around that you have these electrons that have a negative charge. And when everything is really nice and happy, you've got the same number of neutrons, protons, and electrons inside the atom. That rarely happens, and if you strip off electrons or add electrons, you make an ion, and if you take neutrons out or add neutrons, you get an isotope, which is the name of the baseball team that Homer Simpson plays on at work. And you have this kind of a little solar system picture, but it's not really that simple. When you have an electron, it's certain distance from the center, it pops down to the next energy level in, and it will release the energy that it was storing, that kept it up there. And it gives off a little bit of light. We see that happening in the projector, we see that happening in the light bulbs in the room and your watch and your iPhone and everything like that. Electrons being excited and giving up energy and giving up light. And the reverse happens. If you pump light into an atom, it pops a little electron up, and the atom acts like a little energy battery, kind of holding it in there. Now, here's our first hint that something weird's going on, so that this electron doesn't go down from one energy level to the next. It vanishes and appears at the next point without passing between, and that's space between the 2 points. It's instantaneously in a different location. That is a quantum leap, which goes to an old 1980s. Someone locked in the bathroom? Oh, we got a little one. Everything's okay. So that's the idea that was used in that Quantum Leap TV show, kind of, not really. But that's where the term comes from, that little jump. So there's something strange. I mean, if I step over here, I definitely have to go through all the distance between. I can't just vanish and reappear. So little weird, little creepy. And electrons are actually in weird shapes called orbitals and found in these little clouds. And that's a picture that's a little closer to what's happening inside atoms, but that's not where we're going to concentrate on in this talk. Never trust an atom, they make up everything. So, that's a great one. All right, so we got these ideas, these little balls sitting inside the atom, these little teeny ball electrons going around. That's really nice. We have a nice word for that, particles. So, and that matches our intuition on how things work. So if, say, photons are particles of light coming from the light bulb over there. that's easy to imagine how they work. Here they come streaming down, they bounce off of me and go to your eyes, and you can see what I look like. And very nice, very clean picture. So if I let a bunch of photons go through a hole, I would get a nice little circular spot of light. And life would be great, right? If I let the little particle go, it would bounce and head off in a different direction. These are all the things that you're used to seeing in day-to-day life. So photons, neutrons, electrons, just particles. That should be the end of my talk. Good night, everybody. It's not. Because if you put two holes in a wall, which is, that's not a big change in what we just did with one hole in the wall, and you let the photons come roaring in and go through the slits, they should make two spots on the wall, right? Is that comfortable with everybody? Yeah? It doesn't work that way. Sorry. It does something like this. Whoa. In fact, the brightest location for all the photons hitting the screen are right behind this section of wall. That's wrong. But this is called an interference pattern, and this is what you see. I could do it if we had a little diffraction grating in this laser pointer. I could make the pattern appear on the wall very easily. It's an experiment that freshman physics students, as I did in college physics. So it's very easy to reproduce yourself and see this. And what we see happening is light is acting like a wave. So you got all these nice waves coming along, boom, it hits two holes, and it starts spreading out just like waves in the ocean going through breakers heading to shore would do. And so you got these now weird little curved waves coming off. It's kind of like these are new emitting points for the light. And wherever the top of the waves, the bright parts of the waves overlap, you get something bright. Where they're furthest apart, you get a darkness. So you get waves adding together, waves subtracting from each other, and you get this crazy pattern like that. Okay, that's strange, but so if I put one hole there, I get photons. If I put two holes there, I get waves. What kind of material does that? It changes its nature based on how I observe it. That doesn't make a lot of sense. So here's the light coming through and a little more realistic picture of light making these bright and dark patterns over here. So light being a wave and a particle. I mean, waves are waves and particles are like rocks. These are very different concepts. How can light do both things at once? Well, this is called wave-particle duality. Someone once tried to coin the term wavicle, and that didn't stick, so don't go with wavicle. Because it's not, these are not compatible ideas, but yet that's what light's doing. And what makes things worse, I mean, photons are massless little particles, so maybe massless little particles do strange things. But these protons, electrons, neutrons, and like that, they're going to behave nicely. Well, they don't. Photons act like waves and particles. Electrons do. Okay, well, electrons are single points maybe, and you could explain that. Uh-oh, neutrons are made up of little things called quarks. So a neutron and a proton are something that have three things inside them. But protons and neutrons make the same pattern. If you send a beam of protons towards two slits, all you have to do is make the slits closer together, but the pattern still happens. And we've even done it with whole atoms. We have shot atoms at a double slit, and we get the interference pattern again. Okay, well, atom's pretty complex. I mean, you've got electrons, you've got protons and neutrons. What's going on here is really weird. I mean, you've got this construct with electrons and particles in the core of this atom, and it's not dividing into two and going through both slits like a wave and then recombining. That's not happening. We're not breaking apart the atom. We're not breaking apart light or electrons either, but they act like they're going through both slits at once. Well, we've even done it with a Buckyball, which is 60 carbon atoms. We fired at a double slit. And the world record right now is a 810 atom molecule made of carbon and hydrogen that's 10,000 times heavier than a hydrogen atom. We've fired a beam of that at a double slit, and we get the same either particles if we observe it one way, or waves if we do it the other way. All right, at this point your head should be feeling funny. So right now you should feel, is this John making sense? No, I am not making sense. But this is what observations show. And what the current research is working on is trying to get a virus or even a whole bacteria to fire through the double slit and see the same thing happening. And we fully expect that to happen. In fact, the virus thing may have been done, because I haven't looked in the last year to see if they've done the research. That's a really complex thing. And it's going to go through two slits, but not get destroyed, but act like a wave, but also be a particle. Ugh. So our intuition is happy with electrons being little balls that hit a wall or an electric field and bounce back. But as a wave, an electron hits a wall, and when the peak is there, the most probable place for the electron to be, makes it to the wall, oh, there's that little teeny tail sticking out the other side of the wall. That is the probability, if that's 100% right there through the whole thing, that the electron actually is on the other side of the wall the moment that it's supposed to bounce. And so maybe 10% chance it's going to go through a solid wall. Now you go, well, that's crazy. Now you're really talking silliness. But pull out your iPhones, everybody, and look at the computer in the back. This is semiconductor technology. Semiconductors, silicon is a really nice wall that electrons have a very predictable reaction with. We know the percentage of times they're going to go through and not go through. We control that, and we make really powerful computers that we walk around and play. Well, I just downloaded Sims because it was free from Starbucks, and so now I'm addicted to Sims. So thanks to the electron going through solid walls, I'm wasting time on Sims. So when we look at a particle like an electron or a proton or an atom or a molecule, we actually have to deal with where it probably is, rather than it really being in any one place. In fact, Heisenberg found out that we really can't know exactly where any of these things are. If we know exactly where they are, we don't know how fast they're moving. If we know exactly how fast they're moving, we don't know where they are. And there's no way to break through and get past this fuzziness in reality of subatomic particles. So back to our picture of an atom, an electron is kind of there or someplace around its orbital. It's not like a little planet going around the center star. The center star is kind of there and kind of not, and same thing with the electrons. That's a better picture of what's happening inside of atoms. And everything is a wave. It's called the de Broglie wavelength. You can figure out how uncertain you are with a simple equation that I don't have here. But if you take a look at you and calculate how uncertain you are, 10 to the minus 37 meters, that's smaller than that last frame in the video I showed, the Planck scale. So you're definitely there. You're not fuzzily there. There is some probability that if I lean against the wall, I'll pop through, but it's billions and 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 billions, billions, trillions, trillions to one chance that I'll do that in the next billion years. So I'm not going to count on it. So, and you can figure out what the wavelength of the Earth is, 10 to the minus 63, and the whole universe is even smaller. Yeah, you don't have to worry about your waviness. So let's go back and look at the scale of things here again. So back to the atom, here's our nucleus, here's our electron kind of clouding around. Go down to the nucleus, you got your neutrons and protons. Inside of a proton, you've got three things called a quark, which we can't pull a quark out and look at one, because the more you pull, the more it fights back. It's kind of weird. So you got a quark, and then you got these little electrons down here. Quarks and electrons, as far as we can tell, are single point entities. We don't think that you can break them into other particles, but maybe so. That is an active area of research right now. Forces also have particles. We got gravity holding you down nicely. The graviton, which we have not observed, would be, if it exists, the particle that communicates the force, trust the force, Luke, of gravity. The weak force is number 2 on my list here. This is the force that helps parts of an atom nucleus pop out. It gives you the effect of radiation, so that's bad, but you've got radioactive particles in you, radioactivity out of the ground, radon in your basement. So you're surrounded by stuff that indirectly is affecting your life through the weak force. You have the photon, which we just talked about, little particles of light that transmit the electromagnetic force. That's the one that kind of makes all of reality around you. The fact that your skin is a solid surface, or the floor is holding me up, or that there's atoms with air that I can breathe, or that I can see, or my neurons are firing and with electrical chemical impulses, is all electromagnetism. Just about everything you have a name for, except gravity, is related to electromagnetism. That's the world you live in. Deep down inside of the atom, the strong force, it holds the little quarks together inside the proton, and also helps hold the nucleus together. And the transmitting force of that's called the gluon. That's easy to remember. Glue holds things together. So 4 particles of that. So one of the big pushes in physics is to try to figure out how all these forces may be one force. We call that the grand unification theory. That's one of the big desires in string theory, is to take these 4 forces we see today, run the clock back to the very beginning of time when the universe was really dense and super energetic, very hot, and see how these forces merge back into one original force. And we have the nuclear weak force, we have the we have the grand unification force trying to bring the strong force in. We're trying to get the theory of everything that brings gravity in. That's some of the work being done at the Large Hadron Collider, France and Swiss border, but we're not here yet. We don't have this figured out. Gravity is really weak and really elusive in all these. But here is all the little particles that you saw drifting by in the video, organized a little better. So you've got purple things are called quarks, the greenish things are called leptons, the 4 forces are right over here, and the brand newly confirmed particle that helps give mass to some of the universe is the Higgs boson. That made a lot of news over the last couple of years, and that was the big crowning achievement at the Large Hadron Collider, is to narrow in on some of the properties of this hypothetical for 40 years particle. The up and down quarks are what makes neutrons and protons, and these other quarks do other weird things that I'm not going to get into in this talk. The electron is our little particle that we're used to being on the outside of the atom, and I'm not going to get into the other leptons because that's beyond this talk. But this is pretty amazingly small number of critters in this zoo for all the strange things that happen out there. And all of these are acting weird and quantum mechanical because they're all little particles. So here we go to part 2 now of the talk, where we see how physicists deal with this strangeness. How do we go from waves to a world that makes sense? And the 2 leading theories are the next 2 parts. The Copenhagen interpretation and Everett's many worlds interpretation. And there's other attempts out here, but these are the 2 big ones. So here's off to Copenhagen. In Copenhagen, what they look at is this big wave over whatever you're looking at. This could be an electron, this could be a proton, this could be an atom. It could also be any feature of those little particles, their energy, their position, their velocity. Particles have something called spin. I mean, you can pretend that it's like this, but they're not really spinning. It's another one of those words, but it is a quantity that we can measure. In fact, future computer technology will probably use spin in memory. Polarization, you use this every time you go to the movies and see Hobbit or Marvel movies in 3D. So we use polarization to give you that 3D effect, because the screen is either circularly done this way, or one side is horizontal and the other side's vertical in the way that the light waves are waving. And so all of those, whatever feature you want to give to these little particles, initially when you're not looking at them, there's some fuzzy wave. Who knows exactly what they are? As soon as you make a measurement, boom, it pops into the answer. The polarization is up and down. The spin is this direction and not the other direction, or it's this direction, or whatever. It is said to collapse. Once you observe it, it collapses into the observation that you see. That's the core of the Copenhagen idea. So that brings us to Schrodinger's cat. So Cat in the Box by Dr. Schrodinger. In your quantum box, maybe. So the internet was invented for cats, by the way. I don't know if you guys knew that. So Schrodinger took this idea of collapse and fuzziness before you make an observation and turned it into this thought experiment to try to challenge his fellow physicists to think about what's going on. So here we have his experiment. Now, no actual cats were harmed in this experiment. Better not have been. So here's a kitty cat in a box. And in here is something that is quantum mechanical in nature. It's a chunk of uranium. And the weak nuclear force is going to cause uranium to break into some little particles of radiation. Some of the neutrons and protons will come out. And you put a little Geiger counter over here that's watching, waiting for that moment that a particle comes its way. And it triggers a hammer that falls down on a vial of poison, and the kitty cat dies. Oh, kitty. All right, so that's his experiment. So you know, well, so why? We're thinking about hurting cats. What's the deal with that? Well, before you open the box and see what has happened after 1 minute, or 5 minutes, or 20 minutes, this is a quantum mechanical entity, this little lump of uranium. It is both decayed and not decayed. It has happened and it hasn't happened, and as minutes go by, the chance of it happening has increased. And so it is really legitimate in this interpretation to say that the lever is both up and down, increasingly down as time goes on. The poison is both broken and not broken at the same time, but increasingly more likely broken as time goes on. And the cat is both alive and dead, but increasingly more dead as time goes on. What does that mean? So that's the strangeness. Now, these are physicists trying to figure it out. So if you didn't like waves and particles existing at the same time. Well, here you're taking that same idea and turning it into a cat that's alive and dead at the same time. We call that entanglement, and that also goes to other phenomena that are all related to this fuzziness that exists until someone opens the box and observes. Now, as soon as you open the box, the probability collapses and you have a cat that's either or not. So we have seen quantum mechanical processes with the human eye. You can't do it here because these are just pictures, but this is a little spot in this piece of metal that's both up and down at the same time. This is vibrating and not vibrating at the same time. And people have looked at it and actually had their thoughts live connected to a quantum fuzzy state. And I don't know what happened to them. I think they probably went to lunch after that. But it is something that we have been able to extend up to the edge of perception, and that's kind of disturbing, so at least to me. So we have this experiment can go further, and you can take this to an absurd length. So let's say you send a graduate student in to open the box. So graduate students are expendable, of course, so you send the graduate student in to look, and right before the graduate student opens the box, you slam the door. All right, now if you agreed that he was going to open the box in 1 minute, you look at your watch, as soon as 1 minute happens, your graduate student is both alive and dead at the same time because there's poison in the box. And of course, you can go, all right, I'm going to peek in there. Bill! But before you do that, someone shuts the door over here, and now they don't know, and you become entangled in the system, and it becomes weird. So when does reality happen? When does this observing start mattering? And you know, once you've closed the door on him, he's as good as just being part of the system. He's just a robot. So it's weird. Now, we can go back to our double slit experiment and see some more effects of this observer. So you got your light coming along, it's hitting the two slits, it's making the pattern. We're bored with that now. But as soon as you put a little observer here, say a little sensor that measures which side the light went, it collapses and becomes just two spots. It goes back to this BB idea that we're most comfortable with. And there's even weirder stuff called quantum erasure. I don't have a slide for this because it gets really weird. But you can make the observation further downstream, and if you do make the observation, it'll be as if the particles went back and went, hey, they looked at us. Oh no, we got to go through with not being a wave. And you'll just get the two particles. Okay, that's a quantum weird world. So the observer, this mysterious phenomenon of being an observer, is important to this. And it helps make reality click into place, it seems. The next phenomena is taking the same idea, two slits, you got your electrons coming along to go through the slits, but you're only going to let one slit go through every minute. Oh, I'm sorry, not a slit. One electron go through every minute. Not a whole cloud of them. You're only going to do one at a time. And you let this run for hours or weeks. And what we get is the same interference pattern. But there's only one electron at a time. How does an electron interfere with itself? Yeah, it just makes my head hurt. So, but this is the type of strangeness that physicists are trying to explain. What do you do with this? Richard Feynman came up with an idea, and that is the every path counts way of looking at it. And so if you're going to look at light going from one spot to another, the best way to figure it out is to figure out all the possible ways it could have gone. And the calculations you get from this really do predict the pattern nicely. So it's an interesting way to go after it. Einstein didn't like this kind of talk at all. This stuff bugged him like crazy. So he came up with his own thought experiment that he figured could break the quantum world. Now, as you'll see in a little bit, he helped launch quantum physics. He just didn't like it. So he came up with the Einstein, Podolsky, Rosen thought experiment. It's another thought experiment. And remember I said that you get a whole bunch of different things that electrons or particles can have that are measurements that are also quantum in nature. And the polarization, whether it's up or down or right or left, is one of those measurements. And what we found is if you have an atom and it lets two electrons go at the same time, one can be up and down and one can be side to side every time. That's great. So you let these electrons go out into the universe and let them go and let them go and let it go, let it go. Okay, sorry. I've got a kindergartner. Frozen is always on the television, so this happens with me. So if you go way out there, you chase this electron or you wait a light year away for this electron to come to you and you measure it as being up and down, and you go, hey, I measured it. I know instantly that on the other side of the universe, or a light year that direction, that the electron or the light is going this way. It's horizontal, it's the opposite. It's great. So if I make a measurement way over there, then I know something about a particle way over there, faster than the speed of light. Nothing's supposed to go faster than the speed of light. The trick is you don't get any information sent that way. To know that it worked, you have to go all the way over here or send an email from over there over to yourself back over there and find out what the electron did. Because the trick is I can look at the light coming up and down and see if it is or not. Or I could change my mind and I could look at for horizontal and see it that way. Or I could look at diagonal. Or I could look at circular. Or I could look at the spin or something. I could change my mind, and on the other side, great distance away, the particle's going to do the opposite thing. So Einstein called that spooky action at a distance. Spooky things shouldn't happen. Well, it turned out that Einstein was wrong. This really does happen. And it's difficult for the Copenhagen interpretation to handle. Some person named John Bell came along and showed that there isn't some hidden physics. There's not some secret wire behind the universe that connects these two particles and makes them act this way. And we've actually done the experiment now. And the world record in October 2013 is 2 photons going down I think it's a fiber optic cable, 186 miles apart, and they were able to see that the two particles did react in this weird, spooky way. So observations say, yeah, the world is spooky in the subatomic way, and Einstein may not have liked it, but that's just the way it is. All right, so let's go to the third part now of the talk and look at the other way that physicists try to handle this spookiness. And in this other way, you can have your cake and eat it and all the other cakes in the world at the same time. The Hugh Everett many worlds interpretation. This is the idea that every moment that a decision can be made, that something can flip this way or go horizontally or vertically, whenever some change or some decision can be made in the world, that the universe splits off and does both. That's very different than the Copenhagen interpretation. So here the cartoon says, you got this boy figure and a girl figure says, would you like to go for a drink? And it's coming towards me and says, sure, why not? And there they have little kids. And the back one, it says, sorry, I'm too tired. And now they're at the opposite ends of the world. So both happen. So if you have a particle that's spinning up and spinning down, in the next instant, it could continue to spin up or it could spin down. An instant later, it could go up and down, up and down. Instant later, each of those can go up, down, up, down, up, down. All of them happen. You don't have to have a collapse of a reality when you observe. It all happens. Okay? Everything is real in this interpretation. All possibilities are continually splitting off. You only observe the one that you're surfing through in your path through these universes that are coming into existence. If you think about it, every single point in space that is a Planck size is either going to have energy in it or not. Each tick of the cosmic clock, which is about 10 to the minus 45 seconds. So there's a lot of ticks per second. And every one of those ticks, and every one of those points, you've got another decision splitting off. So going right back to all these things, energy, velocity, spin, polarization, probability, all of those things, every decision that can be made does happen in a different universe. So back to the cat in the box, instead of a kitty cat that's part dead and part alive, you've got a pathway in which the kitty cat does die and a pathway in which the kitty cat does live each instant that the particle can come out of the uranium and set off the trigger. In our graduate student looking at the quantum box, well, every other possibility happens. Second by second, every one of those splits off. When we have the particles coming to our double slits and observing, well, in this universe we observed, but in the next one we didn't, and the next one we didn't, another one we observed the other side. In some other split off, we observed both, and some other one we didn't build it because we didn't get funding, and on and on and on. So, now this interpretation does help us explain something in quantum computing. In your cell phone, in your laptop, in your pad, you got ones and zeros that run everything. Memory and the programming is all done with these binary calculations. In a quantum computer, you have qubits instead of bits, and these little guys are all the possible values of 0 and 1 at every instant that they possibly can be, all at the same time. Well, in the Copenhagen interpretation, you're able, let me back up. With a quantum computer, theoretically, you should be able to crack any normal security code in seconds or minutes that a standard computer would take 1 million or 1 billion years to solve, because you're doing all the calculations at once. Well, in the Copenhagen interpretation, there isn't time and space in the universe for all those calculations. But in the Everett interpretation, the calculations are just shared across all these universes next door. 10 to the 500 universes are at your disposal for calculating if you need. So back to this weird thing with our one electron at a time, how do we get the pattern? Well, as this electron decides to hit, for a moment it's seeing all the other electrons that could be itself going into all the other possibilities in the adjacent universes that pop off. So it's interfering across all the universes. Same thing with the entanglement problem, is that these two are the ones that happened here, and that all the other possibilities are happening in universes right next door. So which is your favorite? Well, both have strengths and weaknesses. I think there's probably physicists that when they need to for the calculations, will use one. When they need to for the other, they go to the other, or some hybrid idea, whatever is best to get the work done, make the predictions that are extremely accurate. But even if we don't know which way works, or if there's yet to be discovered new physics out there that makes more sense of this to our brains, quantum mechanics is really, by many, considered the most successful theory that science, that humanity has ever created. It explains the photoelectric effect and how solar panels work. It led to nuclear energy. So here's solar panels. Einstein actually helped solve what was called the ultraviolet catastrophe, and in doing so kind of launched this quantum idea and led to solar cells that someday are going to help power everything. And there's Homer Simpson again. Nuclear power explains how nuclear energy works and the geometry of fission and fusion and the energies that go on there. It predicted the Higgs particle long before we had the technology to observe it, but it was there. It shows us that even empty space is foamy and seething with these little virtual particles. Stephen Hawking showed that this is a mechanism that black holes can evaporate with, and we'll do that in the next talk in September. We'll go into more detail on that. So future talks will be special and general relativity for 5th graders, what's so heavy about gravity, information and reality, and I think we probably need to someday talk about nothing. Talk about the emptiness of space and the physics of that. So we'll probably have a talk about nothing that may have a Jerry Seinfeld cameo or something, and we'll do that. So, any questions? Yes.
So when you were back at the picture that had the different particles, and you added our famous Scott particle, is it possible that
that's way up.
things like dark matter, dark energy would then also kind of play to that grid potentially?
Yeah, that would be physics beyond. This is called the standard model, and that'd be physics beyond that. We don't have to the best of my knowledge, we don't have a hole waiting for dark matter particles, but that is a serious phenomena that needs to be explained, and there's something called modified Newtonian dynamics that people have, it's a way to say that normal gravity that Newton came up with stops working in high energy areas or way far away from the edges of galaxies like that. That isn't working well. I mean, there's lots of problems with that. Dark matter does seem to be stuff that has mass, probably interacts through the strong and maybe the weak nuclear force, but doesn't interact with electromagnetism at all. So it's invisible, it's got mass, but we don't have a particle for it. We haven't discovered those yet, but we're looking actively. There's work being done to see, we think that they might annihilate each other and give off a certain level of cosmic ray energy, and we're looking for that and the noise out in the universe. But we're also putting big tanks of cleaning fluid underground and looking for dark matter particles interacting with fluid in tanks. And there's lots of contention about it, whether anybody's found anything yet. So maybe with a large hadron collider up at higher energy, we might find hints too of if dark matter particles are being created, you'll see matter mass coming out of a reaction but not doing anything to some of the sensors, and that would be a nice indication. But we don't have that either, so we're at the edge of science. Any other questions? Are you convinced that it's a strange world down below you? All right.
Thank you, John.
Thank you.